the same fashion where I'll post a link on the Piazza that links to whatever. That links to the Zoom recording. So hold on, I've got a text here. Sorry, okay. Let's see. Well, let me just respond to this email. Okay, let's get right into the final. So, problem one. What is the value of C that will make, this is very similar to the previous one, but what is the value of C that will make the function cosine 2ct pi with periodic with period 2? Well, we know that cosine is t periodic. Is 2 pi periodic. So all we need to do is we need to see that 2ct, since we are making this function periodic with period 2, we want to make this be equal to 2ct plus 2 over pi. Hopefully this is clear. And we also know that cosine is 2 pi periodic. And so what this means is that 2ct plus 2ct, there's a c in the parentheses, so it's going to be a little confusing, but 2c times c plus 2 over pi. We want this to be equal to 2ct over pi plus 2 pi. Essentially, what I'm saying is if I move forward in time by one period, I need this to concur with how the cosine function is periodic. Do we have the recording of the review? Yes, I am recording right now. Again, you're free to leave if so just for everyone who just came in, the meeting will be recorded. I will post the meeting the meeting recording on the link on the Piazza, the same post where I posted the schedule.
Hello. Does the meeting will be showed up on the Piazza and the media gallery on the canvas?
No. So on Piazza, on one of the pinned posts where I wrote down the schedule, you'll see I'll update the post and it'll say like,
Oh, I see the recorded links. They're
yes,
right
and it'll be
next to the
there.
time. Okay.
I just took off the password, so it should work. But please let me know and post in the comments if none of the links work. Are the answers the final all A? Yes. That's okay. Anyways,
Okay. Thank you very much.
yeah, of course. And so I could actually decompose this. And so with these specific types of questions, you have to decompose one of the terms so that it turns into something like this. There we go. Hopefully I did my math right. Okay. And so now we see that I could cancel out two terms. Boom. And we quickly realize that C is equal to pi squared over 2. Hence our answer. Just for those of you who are just in the meeting, I don't know if you were here yesterday or not, but please interrupt me as I'm going through and if you have any questions, because I'm just
I
going
have
to
a
be
question
through
on
this.
this.
Yes.
So why, like, could we also just do 2c over pi is equal to omega? And then we want a period of 2. So then we could just set 2c over
Oh,
pi
yeah.
equal to 2 pi over 2.
Yes, that's also a very valid one. Like again, okay. So I like this method because it kind of like works with the fundamentals of what you learned in week 1, where you're just using the definition of periodicity. But of course, you could also do alternatively. Again, there's never really one right answer, one right solution. We realize that cosine of 2c over pi t yields omega naught, or I'll just say omega, equal to 2c over pi. Then we know that t is equal to 2 pi over omega. And thus, this implies that the period And we also want this period to be equal to 2. And so, what does this mean? This means that 2, I'll just write it all out. 2 over 2c over pi is equal to 2. This must mean that 2 pi squared is equal to 4c, and thus you obtain the same answer. So yeah, so again, there's no really correct answer. It's just that whichever way you're comfortable with. All right, define 3 signals, x, y, and z. Which of these statements is true? So let me see here. So first of all, when I analyze all these 3 signals, my first gut reaction is this is just 2 cosine of t. Furthermore, for this, I could decompose this function into 3 parts. This multiplied by e to the t squared times a constant. There's a constant, so that's that. And let's see, for this one, we have 3 times sinc, 3 times, I'm going to do a pro gamer move here, and I'm going to do sine of 5t. I'm going to make the bottom 5t, and to make sure that's consistent with whatever this is, I have to multiply by 5 again to make sure that it's like consistently 1 over t. And then multiplied by cosine of 6t. So clearly, so this is a question asking whether stuff are even or not. Clearly, this is an even function. This is an even function. This is a constant. Therefore, zt is even. Cosine is already an even function. And furthermore, sinc is even. And cosine is even. And then we have constants. And so with these two together, x of t is even. RP, please, I'm willing to clarify, or actually I'll just show it right here. I'll show you that a product of even functions, let's say f is even, g even, implies that f times g is even. That's not composed, fg even. This is something that's universally true, and I'll show you why. Consider the product. And all you need to do is say, oh, well, this is actually just equal to, let this be equal to h of t. Then we realize that this is equal to h of negative t, and these two are equal. So you have this commuting diagram. Thus, you get these two equal. And so with this, we obtain that all 3 are even.
Can I ask just 2 quick questions?
Yes, of course.
Yeah. So first, how did you turn that sine of 5t into a sinc function?
I see. So basically what I did was I put these two together, and it'll be sine of 5t over t. But then I
Okay,
just multiplied by 5 over 5, and then I put 1 5 on the bottom, and I kept 1 5 outside.
1 5 at the bottom. Okay. And then how did with the bottom function where you had the t squared and the e to the power of negative t squared, how exactly do you know that those are even?
Oh, okay. T. So the easiest way to do an even function test is to check if t squared, let's say you have a function
Is equal to like negative t squared.
exactly, yeah. So we just want to
Okay.
check this. And
That answers
so
my question. Thank you.
yeah, you just like make sure you replace every single t with negative t, and then just check everything.
Got you. Thank you.
Of course. Moving on. Problem 3. If x of t equals h of t, is 4 e to the negative 4t times u of t, where x is the input to a linear time invariant system with impulse response h of t, the output of the system t equals 2. So there's many, again, for any of these questions, you could really do anything. Like there's no correct way to approach it, but obviously there's a way that's in particular nicer than the others. When I look at this question, I immediately think of just doing I don't think a brute force convolution would be nice though. Um, hmm. We could do a brute force convolution, or you'll try a method. We can do Laplace transform as well. I will do just a straightforward approach where it ends up working nicely when you brute forces. My gut reaction for that was the fact that if I do this, it's essentially like I'm doing convolving this with this. Then I guess that's not too bad. I don't know. It's gonna be it's gonna be kind of okay. Okay, well, I guess we could work it out. So, what I just drew out, and actually I'll show you. Hold on. Hold on. There we go. So what I just drew out was my mental image of what happens when I convolve these two functions. And so let me actually draw it out. So one of them will be like this. It's just a shape that matters, not really like the value. So initially I have a function like that, and then I also have a function that's going to be, let this be x of tau. Let's actually let this be h of 2 minus tau. Then what happens? Well, I go from 2, it's 4, so 2. It's gonna be like this. And one of the most important parts to observe here is that these two functions have the same shape. Remember, they're like in that this particular curve will always portray e to the negative 4t, or like have a curve that's somewhat like e to the negative 4t. And so what this means is that we can actually just cut this into two intervals. And this particular, like it's like a reflection where the shape in here is the same as the shape in here. I'd be happy to clarify why that is, but it mainly comes from the fact that we have x of t equal to h of t. So what happens here is, so I'm gonna write my integral. It's gonna be from 0 to, so clearly it's from initially from 0 to infinity, for x of tau and h of 2 minus tau. This is our output y of 2 d tau. And first of all, it's very nice that we could kill off a bunch of the bounds from 0 to 2. And furthermore, in these bounds, we have that it is, in particular, the e to d 4 e to the negative 4t. I guess it's fine. Times 4 e to the negative, oh, sorry, it's not tau. 4 e to the negative 4, 2 minus tau d tau. And so we push forward. I mean, well, okay, you could do the trick where like you kind of split into two. That's okay. But it looks like this integral is actually very not too bad, just as Sam said. So I'm just gonna proceed with that. So I have 16 on the outside, pull out the constants, and I could sum up this inside part where it turns out to be e to the negative 8. Oh, that's convenient. It is negative 8 plus 4 tau again. And look at that, the exponents cancel out. So it's 6 times 0 to 2, e to the negative 8. So hence we get 16 e to the this, and the integral of just that from 0 to 2, which is equal to 32 e to the negative 8. Thus, we get this answer. Not bad. Very not bad at all.
Oh, can I ask really quick how you got the balance from 0 to 2? I get that the 0, I'm guessing I know that the 0 comes from the fact that it's a unit step function, so there's not going to be negative values, but then the 2 is because it's shifted by 2, something like that?
Yes. So if I want to be super duper, so let me put a star right here. If I want to be super duper clear, because I obviously skip some steps. Like whenever I do these kinds of things where I cut the bounds, I'm definitely always skipping some steps. So let's try to be coherent here, because coherence is always nice. I'm gonna have some function. Actually, no, I'm actually too lazy to write all that. It's gonna be some function, and it's gonna be u of tau, and then times u of 2 minus tau. Okay? And the thing is that let's actually cut it up into 3 parts. I'm gonna have the integral of everything, u of tau, u of 2 minus tau. This is gonna be from negative infinity to 0, 0 to 2 of whatever. Oh, I'm writing way too big. There you go. Come on. There you go. Plus 2 to infinity. No, that is not a 2. So this is what we can do definitely by properties of integrals. You can always cut up the bounds however you want. And we realize that in this particular bound, this is always 0. In this particular bound, these two are both 1. And in this particular bound, this is always 0. Hence, you could kill this to 0, you could kill this to 0, and then what you get is just
Okay.
the integral of this bound with just whatever's over there. And
I
hence
got
you
you.
could
Thank you.
obtain just that. Yeah, so this is how you would work around with, especially with like unit step functions. Anyways, good question, good question. It's always good to see how like the simplification works out. What is the Fourier transform of the signal below when omega equals pi divided by 36? Okay. So I'm gonna say that this is just a brute force question because there's no particular, it doesn't look like there's a way to do this really nicely. This is equal to the integral from negative infinity to infinity for our function. Remember, this is just by definition. E to the negative j pi over 36 t dt. This is just by directly, like just what we know. And now we could expand this. Well, we realize that for in this interval, well, from negative infinity to negative 12, it's just 0. X of t is 0. So actually, maybe I'll just write it out one more time. Dt. Actually, no, I'm just going to just do that. So we can split up into 3 parts. And we realize that in this interval, I don't have my little things. In this interval, x of t is 0. In this interval, x of t is always 0. In this interval, x of t is equal to negative 1. In this interval, x of t is equal to 1. Hopefully this is clear. And so with this property, we could just kind of push around and kill off some integrals. And we obtain the simplification as follows. Negative e to the negative j pi over 3. I don't like writing pi over. Yeah, here, let me just write like this. I'll just keep it in general so that I could save off like a bunch of strokes, you know? And so plus, and this is just e to the negative j omega t from 0 to 12. Splendid. Obviously, I want my notation to be right. And now I just integrate. Nothing too shabby. So let's integrate this function. We have 1 over 1 over j omega e to the negative j omega t hold on. We're trying to think below. J omega t, perfect. From negative 12 to 0. Plus, this one I have negative j omega e to the negative j omega t from 0 to 12. Okay, so let's see how this works out. Remember, you're replacing t with these, so it's 1 over j omega and just like e to the 0, so you just leave it at that, minus 1 over j omega e to the negative 12 j omega, plus, let's consider what this is. It is negative 1 over j omega e to the negative 12 j omega minus, and then you subtracting it, so it's plus 1 over j omega, and then you just add t as 0, so you just leave it at that. So hopefully I didn't make any mistakes so far. So far, so good. And now we observe that this is just 2 j omega minus 2 over j omega e to the negative 12 j omega. I feel like I made an arithmetic mistake, but I think we'll probably find it down the line somewhere because I did make an arithmetic mistake. I'm trying to find it. That's fine. And yeah, I did make an arithmetic mistake. Did I? I don't think I did. Negative. I did. I think it's right here. Yeah. The first term should be e to the 12. The first term should be, hold on. When you sub in 1, the first term should be this term. Oh wait, it should be 12. Yeah, sorry. Thank you. Okay, there we go. There we go. Yeah. There's that. There's that, and then boom, boom. I believe I made a arithmetic error here. Hold on. Let me just really make sure. Let me just really make sure that I'm doing this correctly. Yeah, it should be negative right here. Well, e to the, well, let me actually just take the derivative over j omega, this, and I take j omega down, e to the negative j omega t.
I have a question.
Together.
Is that negative in front of the integral supposed to be carried? It's supposed to be carried on, right? Oh, you did.
I canceled it out because
Yeah, when you drop down that negative j omega, cancel it
yeah.
out. That's my bad.
And this must mean that this must be, yeah, I believe this one should be negative j omega. Yeah. I don't know what Never mind, I'm fine. Okay, never mind. I'm doing fine here. This is good. Sorry about that. And so negative 12. Okay, good. Okay, I just double checked everything and everything's fine. So I get this, and I should get 1 over j omega e to the 12 j omega minus e to the negative 12 j omega. So, that looks a little sus, but I'm gonna leave it at that. And now I have pi omega equal to pi over 36. So let's kind of check it out. We have 72 over pi j minus 36 over pi j e to the j pi over 3 minus 36 over pi j e to the negative j pi over 3. And so in reality, we can actually kind of like work with this part where, let me actually factor it out. We have 1 minus pi over this. In fact, we could factor out the semi-36 here. And we have 2 minus e to the, that's fine, I guess. J pi over 3 minus, in fact, I'll actually factor it. There we go. Hopefully that looks familiar. We realize that this is just cosine 2 times cosine of pi over 3. I don't know how that turned into 26, but there we go. 2 times cosine pi over 3, which is equal to 2 minus 1/2, which is now 36 pi over j 3 over 2, which is equal to 54 over pi j. There we
I
go.
believe it should be 2 minus 1.
Hold on. Oh, I multiplied. Sorry, I forgot the 2 over here. So it's 2 times 1/2. Oops. And so it should be 36 over pi j, which is equal to negative 36 over pi times j. And thus we get our answer. Perfect. Thank you for the correction. By the way, this one's very straightforward. I choose to keep it in omega, like in general, because I don't want to write pi over 36 like over and over again. You could plug in pi over 36 early, but you'll find that you're writing out a little more than usual. That just concludes actually the first 4 questions. And you put the questions, or I want to move on. Okay. What is the magnitudes of the impedance of a 25 microfarad capacitor at a frequency 24 kilohertz? Okay, so first of all, it's very important for us to convert this into angular frequency. This means that omega is equal to 2 pi times 24 10 to the 3. And it's 25 microfarads, which is 25 times 10 to the negative 6. And so if we want to find the magnitude of J1 over J omega C, this is equal to 1 divided by the magnitude of J omega C, which is equal to 1 divided, I want to just do in parentheses, J, hold on. So one important fact here is to realize that omega is real, the capacitance is real. This must mean that this is purely imaginary. And so the entire imaginary component is just equal to omega C. So all we need to do is just find the product of omega C. Hopefully that was clear, but we're going to use this nice property where, so you can just get rid of the J. You can leave the J in there, but you'll realize that it's not really that important since we're finding the magnitude for only one particular component. And so I'm going to take a product of C and omega. Well, I'm going to leave a 2 pi because clearly our answer requires like kind of the 2 pi to be separate. And again, let's combine our 24 and 25. We know that 5 times 24 is equal to 5 times 4 times 6, which is equal to 6 times 100. So that's just 600. And so this is 600. And then we multiply exponents together to get negative 3. And then we have this. Okay. So now we have 2 pi. Obviously, everything's a positive number here, so we can kind of just get rid of the absolute value sign. And now we obtain that is a 0.6. Or actually 3/5. And to -1. And so what we obtain is 5/3 times 1/2 pi is equal to 5/6 pi. Voila. Perfect. That's problem 5. Pretty straightforward. You know, most of this is ece35 review. Suppose the output of a linear time invariant system is shown below, shown there, right there. And when the input is delta and delta minus 2. And the output is as follows. Oh, and the output is that when the input is a different kind of input. What is the impulse response of the system? Oh, this is an interesting question. So I'm actually going to draw it out first. So we have a system. We have that. And then we have voila. And so from this point, make sure I'm recording. From this point, we want to find out the impulse response. What is the impulse response? The impulse response, h of t, is the output of a system when you input a delta function. So how can I find the output of the system with a delta function using what I'm given here? Well, it's very convenient that these two are the same. So what I do is I can add these two together. This must mean that delta 2 delta t given to the system will yield e to the negative 2t. Yeah, just e to the negative 2t ut. And so we realize that delta t input into the system will give us, by linearity, this, which is equal to h of t. Thus, this is our answer. Oh, sorry, my neck hurts a little. Oof. All right, that's that question. Problem 7. Define the convolution x of t to be a convolution between two rect functions. What is, oh, you just evaluate that? No. Wait, hold on, this is very trippy. Okay. Okay. So, I'll do this in a very particular way. First of all, it is important to realize that if you're integrating any function, from negative infinity to infinity, this is exactly the same as integrating a translated version of the function. This is true, and hopefully your integration intuition kind of kicks in here. Is like, if I'm integrating over the entire real line and I move my function, I'm still integrating over the entire function. Like, there's no difference. So you could use this nice property. And so what we realize is that if x of t is equal to the, hold on. If I'm integrating over x of t, this must be equal to integrating over x of t plus 5. which is equal to, I could translate one of my convolutions, my convolution, fellas. I change this. This is t plus 5 minus 5, convolving with rect of 3t. This is the time shift property of the convolution, where I put this time shift to one particular side. Hopefully this is clear to everyone. And so with this, now I just have two rect functions that are centered at 0, and I can kind of maneuver my way around how this convolution is going to work, and I'll do it completely graphically. Yes, you may do it algebraically, but it will be hell. Maybe I don't want to say that, but it will not be very fun. So I will do this graphically. I have rect of 3t. Well, this is rect of t over 1/3. It's a very narrow, this is rect of just t. So I'm going to work with that, where I have my function like this. Actually, sorry, I'm trying to think about how I want to scale this. Remember, this will not be drawn to scale, so I'm just going to draw it out. However, I desire. This is 1/2, -1/2, and all I need to do is draw out. So remember that x of t is equal to integral from, let's call this, okay, there we go. Perfect. And so I'm anchoring down f of t. Would it be valid to see that the integral basically is like taking inverse Fourier transform? You can find the Fourier transform of x of t valued at 0 and 269 function value, which is you see that the integral is basically like taking the inverse Fourier transform at omega equals 0. Yeah, you can do that. I'm just covering the case where, so okay, always. This is like in the Fourier domain, this is equal to like some sinc of something times a sinc of something. And you could evaluate this and like this is just x of 0, like the Fourier transform at 0. So yeah, technically speaking, you could do it like that. I'm only doing this method because it will really help solidify like rect function convolution. So, this is okay, this is definitely an alternative. Alternatively, you could do this. But I feel like learning how to convolve with rect functions is also very convenient and will be helpful in the final. So I'm just gonna do it that way.
I have a question.
Yes.
So I understand how you use the integral property because you're just evaluating from -infinity to infinity. So it doesn't matter where you shift the function. You're still integrating over the same area.
Yeah.
But I'm feeling to see how, like, I'm still a little confused as to, it's being, while that function is being convoluted with another function, you could still apply that property,
Yes.
right? Okay.
Yes.
It won't change anything for all cases.
No, it will not.
Okay. Okay, cool. Thank you.
Yeah. And so once I actually draw it out, I feel like it will actually clarify things by a lot. And so now all I need to do is kind of draw out what g of t minus tau looks like. Shoot. There we go. So what does this look like? Well, if, well, this is equal to rect of 3, or say t minus tau divided by 1/3. And so what I realize is that this rect function is basically a rect function that is centered at t and has width 1/3. So here it is. It's 1/3. I want to show 1/3. So if I actually take the real like the real time convolution between these two functions, it will be 0 at up until like these points. Okay. And then if t is between, let's what point is this? This is, oh, it's definitely not drawn to scale. Hold on, wait, let me think. Never mind, it is drawn to scale. That's good, it's perfect. It's centered at from 1/3 negative 1/3 to 1/3. Drawn in purple. It's going to be completely immersed inside. Actually, so for t less than -3 and t greater than 3, we'll have that the blue rect is outside the other rect function. What does this mean? This means that the x of t, if you take the product of these two not overlapping functions, so this means that it's not overlapping. Then the product will be 0. And so x of t will be 0. Nice. Similarly, if t is between these two numbers, let me actually just write out like this. Oh, actually, I think that one was fine. If I have t between these two numbers, then the blue rect always fully overlaps. Sorry, purple. So purple fully overlaps the red. And so the product, this means that x of t, the product of the integral over the product of the overlaps, will be just the area of the purple, which is just let me see what it is. Should be, sorry, this is width, should be height 1, I believe. Height 1. Oh, well, yeah, that's really drawn to scale. My bad. And this is width 1/3, and so rect will be 1/3. And lastly, if it's in the middle, if t is transitioning between -3 to 1/3, I believe it's not -3. Did I really put? Oh my God! Sorry, I don't know why I wrote -3 here. It should actually be something like it should be something like 4/6, 2/3. So if I'm transitioning between these 2 points, then what happens is that my rectangle is, as it travels, it's linearly increasing in area. So this is how do I put it? So how I would draw x of t is as follows. Maybe I want to add a new page. There we go. Let me just add a new page. Add page. Perfect. Linearly increasing overlap. And so what this means is that if I draw out x of t, then initially I write out my blue region where it's going to be 0 from everything outside these points, because this is exactly when my rectangles aren't overlapping, which means that the product will be 0. If it's inside a particular region, then it'll be 1/3. And lastly, in everything in between, it should be interwoven very linearly. And so this is x of t. Or, sorry, this is x of t minus 5, t plus 5. X of t plus 5 is this particular curve. And the question is like, why am I doing all this? It's because I mainly want to show you like how you want to think about convolution of rect functions. It's just good practice. Okay? And so now, all you do is find the area of this. Hopefully this is correct. And so the area of this would be, I think it's actually off by a little. It's width 1. Actually, no, its height should be 2/3, I think. X of t should be 2/3. Hold on. 2 times rect. Yeah, it should be 2/3 right here. There we go. Yeah, sorry about that. And so this means that this trapezoid is just 3 parts where you kind of move this triangle over here. And then you have just obtain a height 2/3, and you obtain a length 1, width 1 rectangle. And so it's just 2/3 times 1, which is 2/3. So no, you don't have to do it this way, but it's good practice to kind of see how it works. As a comment said in beforehand, all you actually want to do, or you can do, is just take the Fourier transforms of the convolution, and then all you need to do is obtain x of omega at 0, at omega equals 0, and then you would be satisfied. So, both ways work. This way obviously kind of takes a little more time, but for me, if I first immediately saw this question, I would just take my rect function approach, because convolving rect functions over time becomes very, very easy if you've seen enough. So yeah. Anyways, hopefully if there's any question, I'd be happy to clarify. But anyways, problem 8 now. Suppose the output of a linear time invariant system is e to the negative 2t over negative 2t ut, when the input is e to the negative 3t ut. What is the impulse response of the system? Okay. And so if I input x of t here, so let's call this x of t. So this is y, this is my output. This is my input. Then obviously my diagram looks something like this. And I want to solve for h of t. I'm going to analyze it in the frequency domain. I have my friend help me, and can you hi, my friend help me x of t convolve with y of t as integral. how did I get the rect graph again? So basically what I did was I thought about, so first of all, it's very important to understand that a convolution is just taking the product between a anchored down function and a function that slides across it like this. And oh, and then actually this is a perfect opportunity to kind of think about that. Let me actually redraw it. I have a rect function that is anchored down right here. And what I do is I draw, this is tau equal to t. Let me make sure that this is, and my blue function corresponds to h of t minus tau. Essentially what I'm doing is I'm seeing, and the value is equal to the integral over the product of, remember it's like our red function, I'll just call RT times our blue function BT dt, right? It's red and blue. And essentially what I'm doing is when I'm doing a convolution is I'm basically sliding this function where t is located. So as t becomes like closer to, I guess I should probably label it. I'll label this as 2/3. I'll label this as 1/3. I'll label this as 1/3. And that should be, those should be negative, I understand. Hold on. There we go. And maybe I'll draw a nicer rect function. That's a little too big. There we go. And so what I'm doing is the value of x of t, the convolution between these two functions, at a particular t is where I just plop down my function, I translate it over here, if it's negative 2/3, and I take the product of these two functions. Take the product of these two functions and realize that there's no overlap. So therefore, the product will be 0, and thus my convolution between these two functions will be 0. That covers this part. That highlights this part right here. Now let's keep moving. Now, as my rect function, as my sliding function moves deeper into my blue-red function, it is realized that the height remains the same. Like the height, like the height of the product remains the same. It will always be 2. But the only issue is that my width is increasing. Like look at the overlapping area in the middle here, right? Look at the overlapping area in the middle right here. We see that this area is increasing. In fact, it increases linearly. And which is why we could say that in this region, we just need to interweave it linearly. So all we know that's linear, I just don't know up to where. Now, if we think about if t is in this kind of region, we realize that now the blue rectangle is completely immersed inside the rectangle. So now all we need to do is, and then now it's going to be constant in every single one of these points. If t equals negative 1/3, t equals 0, t equals 1/3, like everything in here, we observe that the product will be the same. The product of the two functions will be the same. And so taking the integral will yield the same area. Therefore, when I have this tau equals t be inside of this region right here, I could say that it's constant. And then everything follows after, and then the process repeats. And so what I did was I basically drew out this line, I drew out this line, and I drew out this line. And then what I did was, okay, and I know that in the between regions it's linear, and I retrieved this trapezoid. So it's this kind of like, it's 0 here, it's 0 here, it's not 0 here, but increases linearly. Oh, it's constant over here. All these kinds of notions that you have with the rect function will be very, very helpful. How do I get the trapezoid height of 2/3? I got it because where is it? Where is it? Here it is. I have it 2/3 because Sorry, oh, I made a mistake. This is a mistake. The height should be 2. Actually, the height should be 1. We have that the rect function, this rect function is height 2. And the inside rect function is height 1. So the height will be 2. And so height of this is equal to 2 if overlap, 0 else. And then if the small rect function is completely immersed, then we observe that it will be width 3, 1/3. Therefore, we could see that it'll be the entire area will be 2/3. Just to make sure the second rect function is given from. Yes. So I had a direct message saying, and then yes. So basically, you're considering like the bounds. Sorry, this question is going a little long, but I really want to kind of solidify how you would think about convolutions in time. My friend, help me even identity integral x of t convolve with y of t, integral of x of t times integral of y of t. And I'll be able to get the correct answer for number 7. That is hold on, I got a comment saying that the convolution the integral of the convolution is equal to the integral times the integral. I was able to get the right answer. Is this right? That's really hard to say. Basically, you're doing this. No, I don't think that is true. Actually, I think, yeah. I think, okay. This is a very contrived argument. Because essentially what we're doing here is we assume that this is less than infinity. Then what we can do is we can actually switch these orders of integration. This is actually not like an easy argument to make. So what we're doing is we integrate over t first. And now we realize that with respect to t, we could pull out the tau. And now this is actually just the integral of just y of t, so we can actually kind of just get rid of it. And then like you could kind of pull stuff out and doesn't just get the same answer. So I guess that is true in some cases. I wouldn't rely on it though. You have the max value of one shape within another. Yeah, area property of convolutions. It's like that makes the height of the trapezoid 2/3. The height of the trapezoid is not, it's like this particular section corresponds to when, I should draw in purple, corresponds to when I do something like this. So the values of x of t between these 2 points, the values of x of t between these 2 points is entirely contingent upon just this. My purple rect multiplied by my blue rect. And as we soon realize that if, okay, hold on. Let me just, okay, just whatever. It's just this. Well, in particular, whatever, I'll just do like this. it's just the product of the two functions that we're just multiplying. And this, we realize it's just integral of 2 times pt, which is just 2/3. Yeah. Thank you, Drew. Area of the property convolution. Yeah, just make sure. Yep. Okay. Yeah. So does that clarify where I get this trapezoid here? I'd be happy to reinstate any explanations, or you could just come back to it later afterwards if you just want to keep note of it. But otherwise, I will keep pushing forward. But again, all this is exercise. A significantly simpler alternative, simpler. A simpler alternative is to just take the Fourier transforms of these two functions, which are sinc functions, and then just solve for the product of the Fourier transforms and take the evaluated at 0. But otherwise, we just keep going. Problem 8. So right here, we put into the frequency domain, and then we realize that x of omega is equal to, please correct me if I'm wrong, it should just be 3 plus j omega. And we input it. To obtain h of omega is equal to 3 plus j omega equal to 1 over 2 j omega. And so thus, this means that h of omega is equal to 3 plus j omega divided by 2 plus j omega, which is 1 plus 1 over 2 j omega, which is equal to, and then we take the inverse Fourier transform of that. So h of t is equal to the delta function plus e to the negative 2t ut. Thus we obtain our answer. So this is a very standard question. Moving on. Part 3. Okay, so we're a little behind schedule.
Wait, can I ask a
yes.
question really quick about the last one?
Yes.
Was this, did you just get, when you took your x of omega, h of omega, did you just take the Laplace transforms and then just replace the s with frequency?
Yeah, I mean, okay. Yes, you could do that. I just understand that e to the negative at ut has transform of this.
Yeah, no, I get that. That's what I'm saying. Okay.
Yeah. And
Just say that's the Fourier transform. Okay,
Yeah.
never mind. I see what you mean. Thank you.
Yeah, I mean, both ways work. It doesn't really matter how you do it because it'll give you the same answer. And there's no like conceptual difference between the two. It's the same. X of t is the real-time signal shown below, and its Fourier transform is x of omega. What? Okay, yeah. What is the value of... Oh, okay. So let's just work this out directly. This is equal to... Well, okay, actually, maybe I want to write out a little more detail before I do anything drastic. We know that this is true. This must mean that this is true. Which is equal to this. And now we need to just solve for whatever that is. And it is evident that this is just equal to negative 2 pi. Voila. Next question. Number 10.
Wait, can you go back to that real quick?
Yeah, of course. Sorry. I am definitely going very fast, quickly. So all I did was I rearranged the definition of.
Is there any reason why why exactly did you take x of 0? Is it just to make the calculation easier?
Well, the thing is that we want to solve for this, and this is precisely just when x is equal to, like when x is equal to 0, we could recover this integral by setting t equal to 0. Like t equal to 0, then we could, when the x of 0 is equal to 1 over 2.
Oh, I see. So because okay, so since the question is worded where you don't have an e function, you're just taking the integral negative infinity to infinity of the Fourier transform. You want to find where e turns into 1, and that would be at 0.
Correct.
Okay. Thank you.
Of course. All right. And so let's actually, okay, so yeah, that's, you'll see a lot of these tricks that happen. Like it's a very common trick where if you want to take the integral of even like x of t, well, integral over x of t, then this is equal to x of just 0. Because we understand that x of 0, sorry, x of omega, the Fourier transform, is equal to e to the j omega t dt, negative. If we set omega to 0, then this just goes to 1. And then we just get the integral of this. So it's like, this has been used multiple times. So it's a very neat little property. Suppose system 1 produces an output of x of t ut when its input is, okay. So system 1, I always like to make a diagram, especially with regards to these systems. Okay. And system 2 produces an output of that. Which of the following statements is true? Okay. And so, I would like to do it in this kind of manner. So let's say, so linearity, electric linearity. System 1, system 2. It's very clear that if I have A of t plus B of t, I lied. If I have alpha times x1 plus beta times x2 input into the system, then what I obtain is alpha, so like exactly what I put in, all multiplied by that. And this immediately gives us, this is immediately equal to alpha x1 ut plus beta x2 ut. Oh, I forgot to say that. Apologies. x1, x2 will yield y1 and y2. And this is precisely equal to alpha y1 plus alpha. Voila. And so we obtain this kind of result. And so we basically showed that putting x1, x2, a linear combination of them, will get out an exact linear combination of the outputs. So good. And same applies for u negative t. So we checked linearity. Both of them are linear. Good. Let's check time invariance. For time invariance, all I will do is I'll say, okay, I'm going to input x of t equal to t. Then what do I get? What do I obtain? I obtain x of t times u of t. So essentially what I'm saying is I'm going to input this, and I get out this. Pretty straightforward. And now consider translating this function. Well, if time invariant, then inputting a translated version of my function. You could remember, you don't need to draw it out. I could just do this in my head, or you could just do this in your head. If you translate this, or actually, I'm going to translate it like this. Yeah, we'll translate it like this. Let me draw my arrows too. Then inputting this into my system should give me a translated version of that. And so it should just give me this. If time invariant. Time invariance should tell me that. If I translate my function by some t0 amount, then my output is translated by a t0 amount. That is time invariance. However, but reality says, reality is that, how much question mark? But reality says that what you truly obtain is not that, but it's just it's just lame. It looks like that. And these two are not equal. Therefore, we do not have what we want. Hopefully that's clear. Of course, that is the intuitive way to show it. Of course, there's an algebraic way. And basically all that lies is, and again, and then it's same for. So the same logic applies to that. So you can logic this one out. Another thing is that, if you think about it, you basically do two things. I have an input x of t, and when I'm checking time invariance, I do two things. One, I think I mentioned this as office hours at one time, but in one method, assuming time invariance, what I do is I'll get my output, find y of t minus t naught. So which would be like another specific example would be x of t minus t naught and u of t minus t naught. And then afterwards, you check with you got to do a reality check where you actually input x of t minus t naught into your system, and then you realize that you don't obtain something that's consistent with the time invariant case. I'll just write algebra diff to write that it's algebraically different, but you get the idea. So again, this is like a different way to think about it, but I'd say that the intuitive way is significantly better instead of brute forcing algebra. Let me drink some. Okay. So problem 11. What is the magnitude of the Fourier transform of the signal x of t defined below? And we have, you have this. Wait, hold on. What is the magnitude of the Fourier transform of the signal? Oh, okay. What a great question. Where do I start? So clearly, this is equal to e to the negative t multiplied by u of t minus 2. Oh, the u of t come from the impulse response. Why doesn't it come from the time shift data output? You don't. We never said this was an LTI system. We just said that if I give it x of t, it'll give back to me x of t times u of t. It's not really considering the impulse response. It is just considering like input, and it gives you the output. And so, basically the general rule of thumb is when you assume time invariance, you consider the output and replace every I hate to write this down because it's kind of like it's super formulaic, but it's whatever. I guess I will write it down because it's a not fun way to do it. But when you so I'm going to continue what I was writing here. If you assume time invariance, find your output and replace all instances of t with t minus t naught. And then your reality check is when you find output y of t and replace every single x of t with x of t minus t naught. And that's how you check. And then the time invariance holds when these two are the same. But that's like the general rule of thumb. That's like your formulaic way to consider it. And so in reality, if I gave you, let me put it this way. If I gave you my phone, if I gave you my phone, then you gave me a phone with a sticker, you put a sticker on it. That's the system. Like I give you an object and you put a sticker on it. Like the reality is that if I give you my phone snapped in half, then you'll just give me back a phone snapped in half with a sticker on it. But time invariance says you'll have maybe like half a sticker. So you want this kind of inherent property of the signal to hold throughout the system when you have time invariance. But in reality, you might have a very simple system where you just slap on a u of t. So the reality is that I give you x of t. Like in the reality system, we have x of t. I slap on a u of t. If I give you x of t minus t naught, I don't care that you translated it. It's just a signal. I just slap on u of t minus u of t right behind it. Is that clear? Okay, perfect. Good. Here's the next question. So we realize that we have this kind of system. Okay. And now I just want to find the magnitude of the Fourier transform right here. I could do multiple things. I could definitely do multiple things. In my case, I will just do this. I'll use a time shifting property where I'll consider, hold on. The Fourier transform of x of t is equal to, this is a little shortcut that you'll be seeing, but it won't really matter, will be equal to the Fourier transform of x of t plus 2 times e to the negative 2j t, I believe. Let me make sure that's consistent with what I remember. Yeah. No, it should be positive, I think. Positive 2jt. Please correct me if I'm wrong, but it should be positive 2jt. And so from this point, now this means that x of t plus 2 is equal to e to the negative t plus 2 ut. This is e to the negative 2 e to the negative t ut. Oh, wait, that's a very easy Fourier transform. This Fourier transform is just by linearity, you could pull out the constant. Pardon? X is t be written the other way around. What do you mean by the other way around? Can you
Just
clarify?
just in the definition that you wrote down where it's fx of t, shouldn't it be fx of t plus 2 is equal to fx of t times e to the power of 2jt as like the shifting property? I don't know if what I
Oh
just...
yeah, yeah, yeah. Oh yeah, 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 yeah. This is this. Sorry, sorry, sorry. You're absolutely correct. You're
Okay,
absolutely
thank you.
correct. I did a little bamboozle. Nice catch. So there we have this kind of relationship, and this must mean that action, and then like we could kind of, well, I don't know how I'm just thinking of how to write this. Let's just say this is because I want to save some strokes. We have that x of omega is equal to the Fourier transform of x of t plus 2 e to the negative 2jt. And, well, we know this very nicely. It's just e to the negative 2, 1 over 1 plus j omega, e to the negative 2jt. And then we want the magnitude of this. And magnitude of a bunch of stuff. We could like, it's a product, a magnitude of a product of complex numbers. It's just the product of the magnitudes. I believe that is true. But one definite thing that I know is that this is always magnitude 1. And so I could kind of pull it out. And so now we have this. This is already a positive number. And now we could maneuver our algebra like this. And this equal to 1 over e squared 1 plus omega squared. Voila. Thus we obtain our answer. I'll give it a very short gap. Hold on.
Really quick, how did you take that initial Fourier transform at the top right, e, or what's called x, xt plus 2?
Yeah, so this part follows just from translation. And I basically algebraically pulled out this constant right here. And then I basically, now it's just a constant multiplied by something that we know very nicely, e to the negative at ut, we'll have a Fourier transform of. So it's very nice to kind of like have some of the stuff memorized. Let's see.
Okay, thank you.
Yeah, of course. Okay.
Excuse me.
Yes.
What happened with that e to the power of negative 2jt?
E to the power of, basically I know that this essentially, how do I put it? If I have a product, if I have a complex number times sorry, if I have a product of complex numbers, then the magnitude of those two is just the product of the magnitudes. And the magnitude of any like e to the jt function, e to the j, I'll just say alpha jt function,
It is
equal
1.
to 1.
Okay, thank you.
Yeah, good question, good question. Just check the time. Okay. Hold on. Okay. X of t is the red time signal shown below. Y of t is x of t convolved with x of t. Oh, so you gotta convolve this time. X of t is convolved with itself, then which of the following signals is red? In red is y of t. So there is no shortcut to this. I specifically remember this question, and there's no shortcut, but your intuition in Fourier transforms would help an insane amount here. Rect turns into sync. Like the main issue with that is that you have to deal with a bunch of complex numbers, and I assure you that converting these to recs and trying to take it to multiplication will not be the most fun experience. You have to brute force this. And this is where this is exactly why I like this kind of question is exactly why I did the rect function approach for the problem that we saw above. So I will not look at the answer choices and I'll show you how to exactly do this problem. By saving a lot of time. So let's get right into it. We know that y of t is equal to the convolution of x of t and x of tau, x of t minus tau, d tau. So let's draw our sliding function again, right there. We know that it's centered at 0 like that. So we understand that we have a function that looks like this. Remember, it's translated. Oh, sorry, I could not deal with that squiggly line right there. There we go. We have a function that looks like, I'm sorry, I really want to get this right. So there we go. We have a function that looks like this. This is exactly at t. And I have this function that moves across. And it moves across like this. And basically what I'm doing is I'm taking the product. I got a question. For problem 11 in the way, where is this? X of omega is equal to integral of 2 to positive infinity. That is a reasonable push. Like you could brute force Fourier transform it, where you just take the Fourier transform. I believe that, well, if you were to do a brute force Fourier transform, then what you would obtain is an integral. And then it would be e to the negative t. You kill off everything over there, and e to the negative j omega t dt. And you integrate this, and then this should give you the same answer. I don't particularly see why that will give you the different answer. But yeah, this should give you the same answer. Indeed. Anyways, so back to this intuition. We want to observe the behavior. So I'll actually straight up type it out because I think that'll be helpful. I don't know if I could bring this text down. And I think if I write it, I'll just write it out. My hands will hurt, but we want to observe area of product of blue and red function as blue is translated. This is almost always the way to think about convolution. And so let's us think about it. Obviously, so those of you who are reading the notes, if it may be very unhelpful because the moving animations where I kind of slide around the blue function will be very, very nice. Let's do some highlighting and let's get this going. I will not use red. Let's consider the orange area. So if t is less than negative, oh, sorry, it's less than -2, my apologies. Then the product is equal to 0. So just y of t is equal to 0. That is directly correlated to when we have like the blue function kind of lives over here, where the red function is always 0. So if you take the product, then it'll just be 0. So like it's like this part. Until what point? Until this point. Until this point when the area of the product starts to increase. Until when? I will give you this point. I will claim to you that after, so t, what is it? T equals So from t -2 to some point, let's say -1, the area, well, what is the area? It's -1 times -1. -1 times -1. This is your height. It's like in particular locations, it'll be height 1. So your area will be increasing. So y of t is increasing. Now, let's consider when the t hits -1 exactly. If t hits -1, then we just have two overlapping squares. X of t times h of t minus tau is equal to just a unit square. -1 times -1 in for t equal to for t inside -1 to 0. So it's a square of height 1, width 1, thus y of t will be equal to 1. So we got a point. So if we kind of draw it out, we are getting, let me actually write it out. Boom, 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 boom. I'll draw it in purple. We have 0 everything over here. And then we basically said, oh, at -1, it'll be 1. That's it. That's all we drew. Let's keep going. Now, I'm going to ignore everything from this point because like it's going to be kind of like I'm a lazy person, and so I don't want to deal with how the area changes between these points. But what is easy is when I consider the area when t is 0. I got a question. Why do the blue do mirror each other rather than just the same copy? Is this the property? Is this yes? This is the exact property of a convolution. It's because we're taking we're integrating. Remember, we're integrating over tau and I'm doing negative tau right here, which is exactly why we do that mirror image. Anyways, so this point, if t equals 0, then what I have is that the product is equal to, well, it's kind of like, I'll actually just draw a miniature figure of it just because it's going to be very important to reference. It'll be this multiplied by this. That's not blue. Then tell me, what is the product of this?
Wouldn't that just be 0?
Not exactly. The product will be actually, well, in this interval, it's 2 times -1. Thus, it is -2. So let me actually, this will be -2. I will actually draw it in purple. And then from 0 to 1, it's 2 times -1, which is -2 again. And so now you take the area, y of t is the integral of that, thus y of t is equal to, it's width 2, length 2, therefore it's -4. Width 2, height, sorry, width 2, height -2, therefore you have -4.
How exactly did you get that purple shape where it's the square below height of -2? Because there's no overlap between the figures, I would think that the area of the resulting convolution would be 0.
What do you mean there is no area overlap? It overlaps exactly from in this point, in this interval.
Oh, okay. I see. I'm thinking of it with the wrong way. That's why. I wasn't like literally seeing it overlap. I see how it is.
Oh yeah. So the interval of where the non-zero intervals where both are defined, we could see that it is like there's an overlap. So at this point, we observe that there's a peak. So I'm going to draw it. So down here we have, okay, I have to redraw it to scale, but I'm too lazy. So boom, 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 it should be somewhere down here. And then lastly, I'm going to tell you about the last point of or there's two more points of analysis, but let's say t goes right here. So for t equals 1, we have that the overlap is just between, the overlap is just from like this inside part, this part right here. Overlap in interval 0 to 1 with height 2 times 2 is 4. Thus, y of t will be equal to 4. So it'll be something we're up here. Okay. And afterwards, I take t to be anything greater than 2, and now it's just 0 again, because there's no overlap anymore. So it's this kind of analysis that exactly gives us what we want. And of course, yes, I understand that this kind of took a while because I had to write everything out. But once you see it, you'll be like, oh, I flip function, I place it at these points, and I get my landmarks. And then we'll see the answer is very, very conveniently chosen. So our function, what we did was we plotted these landmark points that are the peaks, and then we basically kind of like drew out the topography of our function. And now I'm just going to interweave it. And what do you know? Our exact answer is that one, which is actually very crazy. And one part of this particular question is that I saw the format of all of these functions, and I was like, oh, I just need to know where it peaks, where it's constant, and where it's not constant. And you'll see that whenever we ever give you a time convolution problem, it will never, ever be something as complex as you think. It will either just be, oh, it's constant over here. Oh, it's linear over here. Oh, it's quadratic over here. That's it. And so given these answer choices, we know that I just need to kind of figure out these landmark points. Or I just need to figure out where it's constant. And I'll be very happy. And this is where the diagram kicks in, where I just need to slide it across and be like, oh, it's here, it's going to be a positive number, +1. Here, it's going to be -4. Here, it's going to be 4. And here, it'll be 0 again. And given these landmark points that I drew, I could obtain the final answer very, very quickly. I'm still a little confused on how you're setting your bounds for t. What do you mean? What do you mean by bounds? I purely did it on the fact that like you mean like my selections of t, like as I like, oh, why did I choose -1? Why did I choose 0? Why did I choose 1? Is that what? Yeah, okay. I chose those numbers. So obviously everything out here and everything outside here, I chose it because it'll be 0. So it's pretty trivial. I chose these points in particular because this is kind of like an inflection point where a square is entirely inscribed in another square, or rectangle inscribed in another rectangle, and vice versa. So the overlap here is like, will be an inflection point where it's gonna like start either decreasing or start increasing again. So this will be like a vertex on the graph. So it's increasing, the area is increasing, the area is increasing, the area is increasing, and it stops. And then starting from this point, the area is decreasing, 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 and it stops because there's this nice overlap. Like you could find the area for the product of these two functions very easily at these points, which is exactly why I did those. So the two reasons basically. I could find the area easily at those points, and B, those are seemingly points where the area would change, like where if I change t anymore, then the direction of the graph will change. It comes with intuition, but we'll see a lot more of these problems in like future final exams, and I think there's another one in this particular practice. But essentially, you think of it as like the sliding function. The sliding function analogy will help a significant amount. If that answers your question, then that'll be. Does that answer your question? Or I will. Okay, I'm glad. Thank you. So yeah, that's how you would do this kind of question. Yes, it is from hindsight very, very tedious. But if you know your your convolution properties pretty well, or how convolution time works, then it'll be very, very easy. So yeah. Remember, the best engineer is the laziest engineer, but not really. Okay. We're actually very behind. This looks like it'll take 4 hours, but what is the value of the Fourier transform of, oh, okay, at omega equals 0? Well, I literally discussed this maybe like 20 minutes ago. X of omega, if x of omega is equal to this, then x of 0 is just equal to this, because the exponential goes to 0. And so all we need to do is find the area of x of t. So let's do that. Well, here's a nice way I like to analyze unit step functions. I basically align them in the order of where they jump. This jumps at 2, this jumps at 5. Whether it jumps up or jumps down, it doesn't really matter. First of all, can we do it in terms of rect functions and convert it into a sinc? I wouldn't recommend it, and you'll see exactly why. Let me actually move this. And so I'm traveling. Oh, I'm at 0. Time to jump. I jump 2. I travel 1. I travel 2. Oh, I'm at 2. I jump down by 1 because it's unit step function minus 1. And I travel a little more. Oh my goodness. Okay. I'll actually redraw this because I drew it very ugly. I'm traveling. I get to 2, so I jump up by 1. Sorry, I jump up by 2. Sorry, I get to 0, so I jump up by 2. I travel 1. I travel 2. I realize that I'm at another jumping point, so I do minus 1. I travel more. I travel 1 block. I travel 2 blocks. I travel 1 more block. Now I'm at 5, and so I jump down again. So at 2, 5, I'm jumping down this. And now what's the area of this? The area of this as well is just 5 unit cubes, and thus we have 7. Voila. So yeah, I would not recommend using a sinc function for this question, because it's not like a nice nice sum of rect functions. Define a convolution. Okay, what is that? Again, this actually boils down to the fast convolution multiplication of fast delta function convolution properties. So I will do that very quickly right now. So we have 2 times delta placed at 1 minus delta placed at 0, convolved with delta placed at 1 minus 3 times delta placed at 0. And so let's convert this. Well, this is, I'm just gonna do FOIL here. This is 2 times delta placed at 2 minus delta placed at 1, okay, minus 6 delta placed at 1 plus 3 delta placed at 0. If people aren't seeing how I'm getting this, actually I'll okay. So you could treat delta functions like polynomials. This was mentioned in a discussion in like discussion 6, where I talked about it. But essentially, when you convolve 2 rect functions or delta functions, convolve, I'll say A and B. This is, well, we know that this is equal to delta of A. Like we have a degree A and a degree B. All we did was we added the 2 degrees together to get our result. And that's what convolution is to delta. Convolution to deltas is like multiplication for polynomials. And so when I'm multiplying this, what I'm doing is essentially I'm convolving these two. I am convolving these two to get this. I'm convolving these two to get this. And I'm convolving these two to get this. I basically just did polynomial expansion, or like your a FOIL technique, but just for delta functions and convolutions. Same exact thing. And so now I realize that if this is my x of t, if I integrate over negative pi over 2 to pi over 2 of x of t, well, x of t is clearly, my signs will be a little off, but that's okay. I have delta functions living at, I have a delta function living at 0. I have a delta function living at 1. And I have a delta function living at 2. My area of integration is from negative pi over 2 to pi over 2, which is approximately 1.5, or like it's a little less than like maybe 1.5. So my area of interest will be right here. So there's only two delta functions that fall into this area, which are these. Integral over, so then this is just integral over this of delta 1, negative delta 1, 6 delta 1, that is equal to. Well, now you're integrating over delta, so they're just their respective constants. And so this is negative 1 minus 6 plus 3, which is negative 4. Voila. Yeah, so another straightforward question. The delta function, remember, I mentioned the delta function convolution trick in the beginning for a reason. It's because there will be, like, these kind of problems will be prevalent. Okay, if the Laplace transform of x of t equals to that Laplace question, by the way, and exists at that point, then what is x of t when t equals negative 1? So, hold on. So we know that the let's see. So this will either have a Fourier transform that is like causal or anti-causal. That is just like our first, like that's my initial gut reaction when I see this question. And we realize that, well, our A, let's kind of identify our A right here. It's S plus A, yeah. So our A is equal to negative 2 plus 3j. The real part of A is equal to negative 2. Hold on. Yeah. And then this means that real part of negative A will be just 2. And so we place our pole at s equals 2. And now we understand that s exists at this point right here. So we have that it must be a causal or anti-causal. I believe this is anti-causal. Let me just make sure that this is consistent. Yeah, it should be anti-causal. So again, now that it's given that it's anti-causal, the anti-causal formulation of this would be, well, the Laplace transform would be equal to just 2 times 1 over s minus, sorry, s plus 2 plus 3j is equal to 2 times negative e negative a, so it's 2 minus 3j times t u negative t And now this is equal to Rx of t. Pretty sure. And so now x of -1 is now -2e 3j minus 2. And that just values 1. So that's our answer. Voila. Question. How did you determine it was not causal, and how does that affect the problem? So I used the fact that use this. You use where it converges to denote causality. It's because if it is converges at here, then it means that the Laplace transform exists right here. Which means that after I determine where the pole is, I have to consider that everything on the left converges because this point converged right here. Is that clear?
Yeah, sort of. Yeah, that makes sense.
Sort of, if there's any like inconsistency, please let me know. Like, or is it just clear?
Yeah, no. I'll ask after. Thank you.
Okay. Yeah, but I'll be happy to answer anything afterwards as well. So let's keep going. Problem 16. Oh my God. Suppose x of t is the input to the linear time invariant system with impulse response h of t and output y of t. The Fourier transform x of t is periodic with in omega with period 2. The Fourier transform is of x of t is periodic, okay, and it's real and imaginary according to shown below. If the system's frequency response is h of omega rect then what is the Fourier transform of the output y of t? Hold on, wait, I actually need to like think. So basically what I'm doing is this is a rect function that is, let me just clarify, this 1 from 0 1 from 0 to 1, 0 else. Okay. Period 2. Oh, okay. So, hold on. Let me just. So we know all we need to do is we just want to find x of omega times h of omega, which is equal to the real part x omega plus j x omega. Sorry, m of x omega. Okay, I really don't have working room here. I'll just write it down the bottom. Imaginary part of that. H of omega. This is quite literally just the real part of x omega times h omega. And so now I'm going to overlay it. Just wait a second, please. So basically what I'm going to do is I will overlay my h of omega to each of the components. I do not know why I wrote it like that. So now it's just this times, it's just, I'll draw it in blue, highlight. This is my rect function. I don't like that, sorry. There we go. And there we go. And so I want you to convince yourself that I have the following graphs. This product is equal to, very simplified version, but it'll just be the following purple graph. Because all you're doing is you're sending everything to 0 except between 0 to 1. And then I want to show you that this is just the following graph. Voila. And so now, after realizing that all the answer choices below are either rect functions or sum of unit step functions. Well, let me see chat. Should write ROC as no, it's because ROC is less than should be greater. Yeah, because the point where it exists is the left of it. Yeah. So sorry, I should probably elaborate that. It's that we have that the ROC is such that the real it's S such that the real part of S is less than 2. Sorry, I should write that down. Anyways, back to this question. We realize that this function is just linear, but it's kind of living just between 0 and 1. So we do u of t minus u of t minus 1. This will give you the rect function that you want. This is like your unit box. Anyways, and furthermore, you get that this function will be your unit just your unit box. And so we put that all together and realize that our final answer is equal to this plus, remember, it's j. Remember, this is the imaginary part. So we need to multiply by j. And then we put that all together. We get t plus j. Sorry, it's all omega. I don't know why I wrote t's here. I'm so sorry. Variable change is weird. Super awkward because you don't see this often. Otherwise, then you get t plus j omega minus. There we go. So, I keep writing t. Whoops. There we go. Let me obtain this. Hold on. Would it be wrong to just make would it be wrong to just make the imaginary graph and to be erect and not in terms of unit step functions? I know what the answer was, but I was wondering if it was okay. So, representing. So you're asking about this part, like why is this part in particular a sum of unit step functions? It's just because the answer choice is set so. Like there's nothing beyond that. How did you turn each of those shapes into unit step functions? It's very helpful to think about this unit step functions. Unit step function at t0 minus unit step function t minus 1 is quite literally just a rect function from negative t to to t0 to t1. It helps to know this and just like intuitively see, oh yeah, that just makes sense. Because you're going up at t0 and you go down at t1, and then it just gives you a rect function. Defined from wherever you want to wherever you want. And so I realized that, oh, this is a linear function multiplied by a rect function that lives from 0 to 1. That could just represent that as a sum of unit step functions, a difference. This is just straight up just a rect function that starts at 0 and it goes down at 1. And so I could just represent it as this. There we go. Yeah, so this is a very nice thing to know. Instead of just writing it down, it's kind of like nice to just work out some examples and see, oh yeah, that just makes so much sense, Anyways, we're not even halfway through. Or are we halfway through? We're not even halfway through, and it's already been 2 hours, so I gotta pick up the pace here. What is the Fourier transform of that? Well, this is equal to remember the property of delta functions. This is a delta function living at -2. Therefore, we just take the exact value of the outside function at t equals -2. And then we're done. And that's it. So now we just take the Fourier transform of this. Is just, wait, hold on. Hold on. Did I make a mistake here? I don't think I did. Yeah, I'm fine. And then essentially what I do here is this a typo? No. Okay, I'll just work it out and I'll see what happens. And now the Fourier transform of this is e to the, please correct me if I'm wrong, but it's to -2j t2j omega e to the -2. And thus I obtain, yeah, I think I'm missing a negative sign. Yeah, well, let me see where I missed out on the negative sign here. Hold on. Plus 2, so it's -2. Yeah, that should be, yeah, maybe this is a typo. Anyone see it? It should be plus and she brought.
Wouldn't the
Oh wait,
transform
yeah.
so we cancels out the negative?
Oopsie, yeah, wait. I kind of made a very big fumble here. I kind of forgot that I can't just bring it up like that. This should be E2. And then you're right. This is actually +2. There we go. So we get that. Yeah, my mistake. Yeah, so I skipped a lot of steps, and skipping steps can definitely lead to fumbles like that. I suggest you leave it like this, and then you evaluate it to be like that. Thank you very much. While is -2 not plugged into the delta function, we have the property that any function is equal to this. This is a property that we learned in class. And basically what it means is that if I have an impulse function living somewhere, and if I multiply it by something, then all it does is just takes the value of this function at this point, but it will still be an impulse function. So yeah. Thank you for the perfect. Anyways, if there's no questions, I'll keep moving. But remember, please feel free to interrupt if you ever have a question. Problem 18. What is the period of the function of this? Oh my. Well, this may be daunting, but it's very important for you to realize that this actually is not a really hard problem. So let's see here. Sorry. We know that this function is periodic with period. Hold on, it's with pi squared, I believe. How about this function? Well, this has a period of, oh, wait, actually, this is just a constant, haha. So we just have pi squared. What do you know? I don't know why I was so concerned about that when there was no t in it. This is a constant, this is a constant. So, one of your freebies, you look at it and like, oh, it's just constants. You get period of pi squared. What is the convolution of two? Oh, another question where you're convolving in time. And these ones are very, very nice. So let's think about this. I'm convolving x of t, y of 1 minus t. Yeah, I'm going to do it like this. Of course, you could do another direction, but it doesn't really matter. In fact, I'll just do tau just for notational consistency. And now let's actually draw out each of these graphs. X of t is a unit step function that goes up at 1 and So it's 1 for t less than 1. So just looks like this. There we go. And how about this one? Well, sorry, how about this one? Y of 1 minus tau is equal to u of 1 minus 1 minus tau is equal to u of tau. Wait, hold on. Okay. So basically for this particular problem, we see that the only thing in terms of t is this particular function. Everything else is a constant. So all you need to do is consider the period of the cosine, and that's it. Okay. Okay, I'm clearly making a mistake here somewhere. Hold on. Oh, I think I made a mistake right here. Yeah. Actually, no, I think I'm fine. No, 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 no. Actually, yes. -9, hold on, 0. Yeah, I think this is a mistake right here. This function is actually 1 for t greater less than -1. Sorry. I think that's the thing that other people may be saying, but guess not. So let me redraw this graph. So that's my u of t function. And my other one is drawn like this. And what do you know? The product of the two functions is literally just 0. Thus, our answer is 0. Can I use this convolution property? Yeah, you can do that too. I don't think it'll be harder. I don't think it'll just be the same. It'll mostly be the. You don't have to. You're gonna just have to be tedious with like moving around the numbers. That'll be probably the only challenge, which is actually not too bad. You just have to be like kind of meticulous with your work. Anyways, problem 20. Suppose a periodic signal. Okay, we have periodic signal is the input to a linear time invariant system whose frequency response is shown below. What is the real part of the output time signal? What a great question. Okay. So let's actually begin with realizing that we're already given the Fourier transform of x of omega. So x of t is equal to, let's actually rearrange this. It is e to the -n e to the j n t. Just from this, we know that's periodic. And from what we know about Fourier series, now we know that, first of all, x of n is equal to e to the -n. That's our Fourier series. And we also know that omega is equal to 1. Sorry, omega naught. We could deduce these two things directly from the Fourier series given to us. And so, what does this mean for us? We know that the Fourier transform of a periodic signal with a Fourier series is equal to 2 pi, 2 pi sum obviously over n and z of xn delta function delta omega n minus omega naught. Everyone following? Is this clear? If there's no questions, I'll keep moving. So given this, now we know that we have a bunch of delta functions living somewhere. We have a bunch of delta functions living spaced apart by 1 to be precise. And all of them obviously have a certain like value associated with them, but we won't care about that yet. And we have h of omega to be rect of omega minus 1. What does this mean? This means that it's a width. What's the width? Width is 1, and it's placed at 1. So what we're going to do, it's basically just this. So h of omega is there we go. That is h of omega. Let me see if there are any questions. Okay. And so now, what is this? So now this means that our output is just equal to 2 pi xn, actually x1 delta of omega minus omega naught, which is just 1. It's clear to everyone? So basically what I did was I realized that if I put my signal x of t into the system, the LTI system, then this means that h of omega will just kill off all of the other impulse functions, except one of them, which is this precise one. And so now I take the inverse Fourier transform, and this must mean that my output y of t is equal to 2 pi x1 is e to the negative 1, and then this is e to the jt. And so what is this? This is actually, no. This is just to get rid of the 2 pi, because we know that e to the j omega naught t has a Fourier transform of 2 pi delta of omega minus omega naught. Using this particular property, we have that this is just x1 times e to the jt, and this is equal to x1 e to the x1, which is just e to the negative 1. Sorry, I'm blanking a little bit. Cosine t plus j, same constant, j sine t. And so now we recover the real part to be precisely this. I kind of jumped around a lot there, but is there any questions regarding this question? Otherwise, I'm going to keep on moving along. Okay. Remember, if you like to keep your questions, then you can ask them at the end, and I'll be happy to answer all of them. What is the value of c that makes the frequency of the function this equal to 10 hertz? So 10 hertz, this means that it's 20 pi omega is equal to 20 pi. And this means we want cosine of t over c to equal to cosine of 20 pi t. And so it's very easy. Cosine is equal to 1 over 20 pi. Voila. Light question. What is the Fourier transform of x of t when omega equals 0? Oh, another one of the same questions. Yeah, so I will omit I will actually rewrite it every time. I think it's just better. X of omega is equal to x of t. I will actually just write from whatever. And then it just means that x of 0 is equal to the integral x of t dt. So now we just need to find the area of this. Well, let's actually graph this out. If it's 2, it's a rect function. So it's a rect function. That's good. 0 everywhere else. 0. And then starting from a certain point, it's just e to the negative t. And so e to the negative t at t greater than 3, it's like, so it's like this. It's like e to the negative t. And this is 3. Is the graph clear to everyone? Does that make sense? So we cut this up into 2 parts. We have the rectangle. And then we have everything beyond that. And so what we realize is that the first integral is actually very easy. It's just 2 times 4, 8. And now we just need to integrate this last part, which is just negative e from 3 to infinity. This is equal to 8 plus negative 0 minus this. And thus we obtain 8 plus e to the negative 3. Voila. Correct answer. Questions? Questions, comments, concerns? Let me just take a drink of milk. Okay. All right. If no questions, I'm gonna keep going. In the circuit below is a sinusoidal steady state. The capacitor is 25 microfarads, inductor is 2 megahenries, and the resistor is 600 kilo ohms. What is the phasor of the voltage at VT? Okay. First observation is that we're given an input signal that is in sine. So it is important for us to convert this into 3. And also omega is equal to 2. 3 e to the negative pi over 2 j. That's our input phasor. And now all we need to do is find the voltage divider for this side. So very easily, we could realize that our output voltage phasor is equal to 3e to the pi over 2j times ZC over ZR plus ZL plus ZC. Not too shabby. So now all we need to do is solve for everything. Obviously, ZR is equal to 600 times 10 to the 3. We know that ZL is equal to j omega L, which is equal to 4 times 10 to the 6. 4 times 10 to the 6 j. And lastly, ZC is equal to 1 over, I'll just say, 1 over j omega c, which is equal to j times 25 microfarads. So it's 50 times 10 to the negative 6, I believe. Negative 1, which is equal to, hold on. So this is just negative j, 1 over 50, 10 to the 6. There we go. And then we obtain that this is just negative j and divide that by 50, which is 220,000? Hold on. Yeah, 20,000. 20 times 10 to the 3j. Okay? And so now we obtained a bunch of things. Now we just need to kind of crank out the algebra at the end. So we leave out I'm just gonna not write the input phasor just because we just need to evaluate everything inside the impedances. And so we obtain negative j 20 times 10 to the 3 divided by, we sum all that, we get 600 times 10 to the 3. And then we add the imaginary parts together. What a shame. That looks extremely not fun to add together. But the imaginary parts should add up to, hold on, microfarad. I just want to make sure that I'm not messing up anything. 25 microfarads. Yep, that's good. Yeah. Okay. In fact, I'll actually do this. I'll convert this into 0.02 times 10 to the 6. I think that'll be a little nicer to work with. 0.02 times 10 to the 6. Yeah. Yeah. And so now I could add these two big numbers together very easily. It is now just 3.98 times 10 to the 6 J. Splendid. And so now, let's just keep doing some math. Let's get rid of some 10 to the 3 stuff to leave out, hold on, negative J. So it's negative 20J divided by 600 plus J 3.98 times 10 to the 3. That's fine. In fact, I'll actually now convert this into our big number. Voila. Let's divide top and bottom. In fact, I think, no, not yet. Yeah, not yet. I'll divide top and bottom by 20. So the numerator becomes negative J. It becomes 30 plus, divide that thing by 20. That is 199. And now we just have to give it our nice little friend here. This is negative 3J. So negative 3J. Now we just give it our all. This is just negative 3 divided by, hold on, I have an extra J here somewhere. Maybe I'm not. Oh, never mind. I did it. I could. So now this is just like an intricacy that we're just dealing with here. But in this scenario, I leave this as 3 over J, and I directly multiply it to obtain. Don't ask why, but now we have negative 199 plus 30J. So we get 3J over. So it's important. So starting from this point, it's up to you to manipulate the variables in order to obtain the answer that you desire that is in the answer choices. So that point is just kind of you fiddling around with the numbers, but we still do get the same answer. And so for these type of questions, if you want to spend the least amount of time, it's important for you to realize that it's like you want to use the magnitudes, these 10 to the somethings to your advantage, and try to simplify the math as much as possible. Anyways, I'm gonna go to the next question. Holy smokes, we have 12 more problems. I think 13 actually. Let x of t be a signal whose Fourier transform is given below, right there. Okay. Wait, what in the world? Okay, let x of y of t be that. Then if y of the thing is a Fourier transform, then what is y of 24? Okay. So, okay. We know that y of omega for this particular question is equal to 1 over 2 pi times the convolution of x of omega with the Fourier transform of sine of 20t, which is pi over j delta at 20 minus pi over j delta at negative 20. And now we want to evaluate this at y equals 24. So all we need to do is actually just directly plug in y 24. Actually, no, we actually can't. I lied. Sorry. Essentially what we're doing here is, okay. we know that x of omega looks like this. X of omega looks like this. It's like down the line, down the line. And then from 40 to 50, it's going to look like a linear function. This is 40, 50. Of course, not drawn to scale, obviously. And when we convolve it with these delta functions, we're basically, now when I do this, I'm shifting one to the left by 20. And then shifting one to the right by 20. Plus 20 minus 20. I mean, well, if I truly want to expand it algebraically, in which I will, I obtain the following. 1 over 2j x of omega minus 20 plus minus 1 over 2j x of omega plus 20. And so everything here is kind of multiplied by a factor of 2j. And so now, I guess from this point, it's actually not too bad. Actually, from this point, you could just actually directly plug it in. And so, kind of lied. Sorry about that. Of course, these are like different numbers, but essentially you have that the x be both sides, so x would be on both sides, right? So like the dash VE part. Yeah, that's correct. Actually. And so what you would see, like visually, what we would see is a pi over j, it's because sine of omega naught t as a Fourier transform of delta of omega minus omega naught plus it's a nice property to know. But actually, I just realized, but starting from this point, you could directly evaluate it. This is just 1 over 2j of x of 4 minus 1 over 2j x of 44. So now this is 0. Let me actually do that in red. This is 0. And this is 2j times 11. Thus, I lied. I think it's actually 11. 22j. Hold on a moment. I lied. I don't know how in the world I even obtained such arithmetic skills, but it's still 22j. There we go. We got pi over j from the fact that of this. So yeah. Anyways, right into the next question. We have a long way to go. What is the convolution of those functions? Oh, well, let's actually take this step by step. This is just delta at t minus 2, delta t minus 2. I will ignore the unit step function, and I'll do this. And this is delta of t minus 1. And then if I combine these two, it's just delta t minus 1. And so this is equal to u of t minus 2 convolved with delta of t minus 1, which is equal to del u minus t minus 3. Voila. Light work. Next question. Oh, never mind. I'll leave it here for a second so that people can see. Sorry, I'm just gonna stretch a little. So, like question right here. Next question. If x omega is the Fourier transform of a impulse train, that's something that we know. what is the integral of that? Well, we know that we could directly recover the impulse train. This is just 2 times. No, I lied. This means that the period is 2. This implies that the omega naught is pi. And so x omega will be the following. So it's an impulse function, impulse train, such that is spaced out by pi, and and then each value has pi in it. And we realize that now we just need to think about how many. Now we're integrating x of omega right here from -5/2 to 15/2. So what that is you're integrating from -5/2. Remember that pi is actually -pi is less than -5/2. And we're integrating all the way up to 15/2, which is actually around 7.5. Then what happens is that in reality, actually, that I actually drew it too far ahead. So equal to 7.5. And now the question is, how many multiples of pi can you fit between these two numbers? Well, you have 0 pi, you have 1 pi, and you have 2 pi, which is around 6.28. So let me draw right here, and then we realize that you can actually fit 3 impulse trains in the area of integration. And so this is just pi plus pi plus pi, which is just 3 pi, each with area pi. So this is pi. Remember, each impulse is area, in quotes, is area pi. And there's 3 of them, so therefore the area must be 3 pi. Any questions, comments, concerns? Happy to answer any. Okay, I'm just going to keep powering through. 27. Define 2 signals like that. Which of the following statements is true? Okay. Well, let's try to simplify this. This is 3 sine of 5t over, I will kind of rewrite it, cosine of 6t. This is equal to 15 sinc of 5t cosine of 6t. And then it's like a single value 0, but like that doesn't really matter. We don't need to think about that too much. And so I'm actually assuming that if t equals 0, then I see. So it's actually a little smaller. Hold on. 7. Never mind. Yeah. So this is a function that basically just looks like. Actually, I'll just leave it. I'll just omit it. So we have the time function that looks like this, and we have a time function that looks like this. Well, this is literally just cosine of t. This is obviously band limited and periodic. Now the question is this. But we realize that a product, so x of t, x of omega, sorry, x of t is clearly not periodic. Because we have a sinc right here. We're multiplying by a sinc function. Now, the next question is it band limited? Well, x of omega is equal to 1 over 2 pi of a rect function of something convolved with like a sum of delta functions. So like, why is that? Well, actually, let me write it out. X omega is equal to 1 over 2 pi. Hell, I would say 15 over 2 pi because I'm going to pull out the constant. And it's the Fourier transform of sinc of t convolved with the Fourier transform of cosine of, what was it? It's 6t. Hopefully this is clear. And so now what happens is this, you have a constant again. And we have a rect function of some sort convolved with the sum of deltas. I will actually write it. We have a rect function of some sort. I'm gonna leave out the middle here, but we know it's a rect function. And we're gonna convolve it with a sum of delta functions. Oh, sorry, my neck is starting to hurt. There we go. Hopefully that's not too many parentheses. And what does this mean? We know that this means that the Fourier transform of x omega will be two rect functions that are spaced apart. It's two copies. One at 6, one at -6. Do you know this for a fact? And so, how do you know that cosine is band limited? Because it's two delta functions. The Fourier transform of cosine will be something that looks like this. And obviously we could like kind of bound the frequency. And similarly with this, we could actually, since we know that it's just two copies of rect functions, we could just we could limit the band, like we could limit the frequency into a certain band. And thus, this is band limited and not periodic, so hence we get this answer. Ooh, okay, there's our answer. Any questions? Shoot. Ooh. There you go. Questions? Is sync never periodic? No, sync is not periodic. I mean, it decays like this, and that already kind of gives it away. It's not going to, like, after it decays, it's not going to rise again. It's going to constantly decay to 0. So, yeah. 28. If the Fourier transform of the signal, that is x of omega, then what is... Oh, this should be very familiar. We know that 1 over 2 pi magnitude of this is equal to that. And so we already know, you already know, this is equal to, oh, and it's actually very convenient. It's just 3t plus 4 from 1 to 2. What do you know? And so I guess I will just normally integrate this. To obtain 6 plus 8, 14, minus 3 over 2 plus 4, which is 5.5, which is 11 over 2. I believe that is correct. 6 plus 8, yeah. And this is equal to 17 over 2. And then now, all I need to do is realize that our desired integral, you have to multiply 2 pi on both sides. So, to the 2 pi. Because remember, we had this little constant. So do not forget about that. This is a constant that is actually very important that you need to not forget. All right, part 8. Almost there. We have 8 more problems. What is the convolution of that and that? Wow. Okay. So we know how to do this. This is another just review question. We have a delta at 1, we have a delta at 0, and we have a delta at -1. We have a delta at 0, we have a delta at -1. Now let's convolve this. And we're doing the same thing as before. Now I'm going to start with FOIL. So if delta 1, or here, maybe I'll be a little more coherent this time around and make it really elaborate. I could convolve this with this. And by bilinearity, what? Hold on, I literally just copied it. There we go, paste. By bilinearity, it's equal to this. Can you go back to problem 28 for a second? Yeah, sure. There we go. Remember, but the notes will always be posted, so just so you know. Yeah. Let's see. Okay, perfect. And so now we could progress with our polynomial interpretation where we just start kind of factoring stuff out. Actually, let me make this plus, and then let me make this a negative delta. There we go. And so let us proceed. Oh, sorry, my neck is hurting. So first convolution, delta 1, delta 0, delta -1, plus, so that's this first part. And the second part, we do the same. It's delta 0, sorry, minus delta 0. Did I hear something? No, I didn't. Minus delta 0 plus delta -1 minus delta -2. And so we now combine all the like terms. It's -2 delta 0. We have 2. Hold on. I think I messed up something. Oh, here's a negative. Spotted. There we go. We cancel out these. And then we obtain the final answer, which is just that plus delta 1 minus delta 2. Wait. Sorry. Oh, this, yeah, sorry, I forgot this part too. So it's plus delta -2. Thus, this is our answer. Voila. So again, it's very, very useful to understand like how to work with these delta function convolutions. It'll be very, very easy for you in the long run. All right, problem 30, finally. I think we'll hit maybe I'll get under the 3-hour mark. Almost. If the impulse response of a linear time invariant system is given right there, what is the output of the system when the input is that? Oh. Okay. So we know that delta of t will give us e to the negative pi jt over 2. We also know that delta of t minus 1 will give us another thing, which is e to the, will give us our original. But then remember that if you translate in time, it is modulation in frequency. And so the Fourier, hold on. So let me actually put it this way. Where do I want to write this? Where do I want to write this, dude? There we go. Okay. So if I input this, then essentially what I'm inputting is in the Fourier domain. So let me actually decompose this one right here. This one in the Fourier domain is e to the negative. I believe it is not negative. It is negative. E to the negative j omega is just e to the negative j omega in the frequency domain. Yes. And so when I input this, what I obtain is that in the frequency domain, my output is h of omega times e to the negative j omega. And now I have this modulated here. I'm going to pull it back here, and then I realize that hold on. Yes, that's good. And I pull it back, and this must mean that in time I have this is h of t minus 1. Oh, and then this should give me just e to the negative t. There we go. So we basically just use, convolution property. Can we just use convolution property of the delta? Yeah, but another very nice thing occurs here where we realize that it's an LTI system. And so what we did was we obtained the output just by changing t to t minus 1. The input of this is just the same output, but we changed t to t minus 1. Similarly, this must mean that if I input this, then my output must be this. So it's like, again, my input-output relationship is that if I put in this, then I get out this by time invariance. Similarly with this. So, and for this like particular plug, I just like showed why it worked out. But we have this kind of relationship. And so we realize that if my input is by linearity, if my input is this and this, then my output must be this, the same sum, which is a little inconvenient in my opinion, but you have e to the negative pi j t over 2 e to the pi j over 2. I'm just like factoring it out. I think this is the negative one actually. And then this one we have e to the negative pi j over 2. Oh wait, maybe I didn't. Yes, I did mess it up. There we go. This is e to the negative pi j over 2. And then now we could factor it out. And wait a minute. That looks familiar. That is just 2 cosine of pi over 2. Actually, hold on. I think I messed up somewhere. Yeah, it's minus. Apologies. This should be minus. There we go. And then this means that this should be 2 times 2j. 2j times sine of pi over 2, which is just 2j e to the pi j t. And voila. Oh, I think I forgot the negative somewhere. Yeah, this should be for my negative over 2. There we go. That's our correct answer. Any questions? So this one uses very fundamental LTI system properties that we learned during class. Okay. Next question. We have 6 more, so hang in there. The signal x of t is anti-causal and its bilateral Laplace transform is right there. What is the value of x of t at time t minus 2 d equals -2? So it suffices to just find whatever the Laplace transform of that is. So let's actually go ahead and do that, or the inverse Laplace transform. So first of all, let's do partial fraction decomposition. This is equal to some number a plus 1 over b times s over s plus 1. And so this means that a s plus 1 plus b 2s plus 1 must be equal to 1. So this must mean that a plus 2bs is equal to 0s, and a plus b must be equal to 1. And so solving this, we obtain that, actually, well, from this, we get that a equals -2b. And this must mean that b equals -1. And this means that a is equal to 2. And so we obtain this kind of result. And now we realize that our poles are at s equals -1/2 and -1. So let's actually plot it out. My poles lie over here. And so with my poles lying over here, I know that the Fourier transform, the bilateral Laplace transform, is anti-causal. It's just completely anti-causal. What does this mean? Well, it means that the region of convergence must lie to the right of all the poles. So we take all of this and all of this. So it's actually kind of important how you kind of perceive this, but we're taking the intersection, like we're taking the set intersection, or let me put it this way. ROC is region that satisfies the real part of S being greater than -1/2 and the real part of S being greater than -1. So it needs to satisfy both. The region of convergence needs to satisfy all of the requirements, not just one. And what that means is that our region of convergence, well, technically speaking, it lies to the right of this and lies to the right of this, which means that since it has to satisfy both requirements, our region of convergence is right here. Is that clear to everyone? This concept is very important. The way you choose the region of convergence is the intersection of all of the regions of convergences, like the individual regions of convergences. So, given this, is it anti-causal to the left of there's no shot. Hold on. I think that you're right. I think I made a mistake right there. Yeah, sorry. Oops. I keep thinking of that to be causal. But, my point still stands, is that it has to satisfy all of the requirements. Voila. Let me fix my numbers here as well. And so now we know that since both are anti-causal, we could find the inverse Laplace transform. So now we know that x of s is equal to 2s minus 1. So actually we could convert that into 1 over s plus 1/2. And s plus 1. Choose s. Yep, perfect. And now we know that if you just use our Laplace transform pairs to find the final answer. Okay? And so for this would be negative e to the negative 1/2 t. Yeah. Minus 1 over, no, sorry. Minus, obviously in parentheses, negative e to the negative t u e u negative t. Hopefully there are no typos. And so now that I recovered this, now I want to evaluate it at t equals negative 2. Well, x of negative 2 will result in negative e to the, oh, that's just 1, so that's e. And then I add e squared. So that should be our desired answer. Oh, this is equal to e times e minus 1. Perfect. Questions? Questions. Okay. All right, 5 more. All right, let's power through, everyone. We're almost there. Let P1 be an impulse train, and let P2 be also an impulse train. Oh, sorry, my neck is also very hurting. If x is t is sinc 3t times that, what is x of omega when omega equals 2.9? What a great question. So for this particular question, it suffices to kind of figure out the Fourier transform just directly, but it's actually very easy. Let's consider P1 of t to be the following. It is impulse train spaced out by 4. Then P2 of t is impulse train spaced out by 4, but also translated by 2. It is very quickly realized that P1t plus P2t is just equal to another impulse train, but it's spaced out by 2. And so now, if we consider x of t equal to sinc of 3t of if we consider x of t, then this has a Fourier transform x of omega that is equal to the 1 over 2 pi, and then it's, well, of course, this yields t equals 2, so this means that omega is equal to pi. And then we want the Fourier transform as the sinc function, which is pi over, I believe it's pi over omega squared, so it's pi over omega rect of 6. I believe this is correct. And we have to convolve it with our impulse train. There we go. Of course, maybe I'll color code it, but this is my Fourier transform of that. And this is my Fourier transform of this. Okay. Yep. Okay, perfect. And so now we realize that this is just copies of, okay, well, actually, let's pull out some constants. And so this is pi over 2, pi over 6 of rect omega 6 plus, convolved with this impulse train. And now it suffices to find whatever this is. Well, it is It is rect functions with width 6 that are spaced out by pi. So if I consider that to be 0 and this is 6 and this -3 and 3, I place another rect function at pi. And I place another rect function at 2 pi. I think it's gonna look something like this. I'm just kind of assuming here, but it should be fair, close enough. And so now we realize that, okay, well, I want to examine omega at 2.9. Well, at 2.9, we have the red rectangle and we have the black rectangle. And so what this ultimately would look like is this impulse, like this convolution. Let me draw it. So this convolution will just look like something like this. Where this is 3 and this is pi. Hold on. Let me make sure I'm not doing any misinformation here. This is actually not pi. This is pi times 2 pi minus 3, I believe. Essentially, it's just gonna look like this, where it's gonna be a bunch of small gaps, and we realize that two rect functions overlap here at 2.9, and so this is gonna be giving you 2. And so if I try to evaluate x of omega at 2.9, it'll be pi over 6 times the value of the impulse train, which is 2. Thus, it will be pi over 3. Okay? This is a rough problem. Like there's a lot of moving parts for this particular problem. So I'd be happy to go over whatever is required. By the way, I'm just gonna keep powering through because we just have 4 more problems left. 3, 4, 5, 6, yeah. If an LTI system with impulse response of that has an input of delta minus 2, what is the output at t equals 6? Well, isn't that really nice? This is a very free question. The output is equal to the two functions convolve with each other, and we know how delta functions behave with convolution. Perfect. And now this means that y f6 is u of 3, which is equal to -1. Boom. Done. No more like there is nothing particularly contrived about this problem. It's just, it's not like an LTI system. You just need to take the time convolution and use the fact that it's a delta function. It's very nice. Okay, suppose x of t is the output to an LTI system that satisfies the differential equations, which is a highlight. Maybe that's important. What is the magnitude of the frequency response of the system at omega equals 1? In order to find the frequency response for this particular system, we just take the Fourier transform on both sides. And we know a property, so what we basically do is we take the Fourier transform of both sides. Maybe I won't do it there. And the Fourier, since the time domain signals are equal, the Fourier domain signals must be equal as well. And so what we obtain is the following. We get j omega, y omega, given that y of t has a frequency response of, or like has a Fourier transform of that. And this is j omega x omega plus 4 x omega. And so this means that the frequency response x omega divided by y omega is equal to j omega plus 4 divided by j omega, which is literally just 1 plus this. And so now we want to see the frequency response of that. So now what is this value? Well, it's just 1 plus 4 over 4 over j is equal to 1 plus 1 minus 4j, and thus the magnitude of this function is 1 divided by 16. I mean, 1 square root of that, which is square root of 17. Voila. Not too shabby. So this one is also just a question regarding taking the Fourier transform of both sides, and what you want to do is you want to use the derivative property in order to solve the differential equation and solve for the frequency response. And then it'll be very straightforward. 2 more questions. X of t is a convolution between, oh my God, what is that integral? So for this question, it's clear that we want to take a convolution. So let's actually just solve for it. Convolution delta at 1 minus delta at 2, delta at 0 plus rect at t. So that rect function is not going to be very helpful to us, but it doesn't really matter. What we're going to do is we're going to convolve our delta functions first and realize that it is just delta 1 minus delta 2. Then we add. Now we're considering this by bilinearity. And we can recover the expanded version of this function by taking this very quickly. Boom, because it's a delta function property. And if every time you convolve something with a delta function, you're basically translating. So we basically translate this rect function by 1, and then we translate this rect function by 2. That's it. And so now all I want to do is solve for that integral. And it seems that this integral will be very easy if I just draw it out. So I have a delta function at 1, or here. I will only draw out the rectangles. No. It's a rect function with width 1 and anchored at 1, height 1. And our second rect function is downward, like that. Okay? And so what this means is that if I take this integral right here, 5 over 4 to 9 over 4, I'm taking the integral from here. So this is 5 over 4, and I'm integrating to 9 over 4. And remember that a delta function lives right here as well. So what is important in this region? We have this, we have this, and we have this. So now it suffices to find the area of all those combined. So if I integrate x of t from 5 over 4 to 9 over 4, then I obtain the negative delta function will give me just -1. And then I will take the integral of the rect function, or like I'll take the integral of the rect function, the combination of the rect functions. This will give me a height 1 width 1/4 and width 1. So we have a height 1, width 1/4, and then we're adding something with height -1 and width 1. So hold on, let me see if I'm just want to make sure that I'm correct here. Am I missing anything? -2, anti-causal, okay. T -2, it's fine. Width of 2, so we have -1.5 to 2.5, that's good. And then, yeah, so this should be good in particular. Trying to see where I have some algebra wrong. Because I'm clearly not multiplying by some certain number. 9/4, which is 2π/4. Yeah, that's good. Oh, my bounds are wrong. Sorry. I'm actually 9/4 should be like right here. Maybe if I drew it bigger, it would have been better. But since I'm integrating between these two, instead my blue rectangle, I'm taking this width, which is precisely 3/4. And so height 1, that's -3/4. And so now this is the it's the red rectangle. And then the blue rectangle gives you this. And so now we could just solve for this area, which is 1 plus -1 minus this minus 3/4, which is -3/2. Voila. All right, last question. Suppose f of t is a periodic signal with period 1, and f of t is like that. What is the magnitude of the coefficient of f2 in the exponential form of the Fourier series? Oh, okay. So this is clearly just a brute force question where basically we're solving for the Fourier series coefficient. We know that the period is 1, which means that omega is equal to 2 pi. So Fn F2 is equal to integral from 0 to 1. So we could integrate over any one particular area, it doesn't really matter, of f of t. Actually, maybe I'll write out the original. Formula, and then I will write out how I will set it up. E to the negative 2 pi, so it's 4 pi j t dt. This is what we have. And we want the magnitude of this coefficient. Well, we just need to solve for this, and it's actually not too bad. We just do 0 to 1, and then we realize that this is a sum. So this is negative 4 pi 1 plus 4 pi j. Essentially, I'm adding the two coefficients together. And I get 1/4 pi j t dt. And now integrating this is actually very easy. I just pull down my coefficient of the exponential, e to the negative 4 pi j t, evaluated from 0 to 1. And now I just directly solve. And so, what can I skip here? I can't skip anything, unfortunately, not yet. So let's actually just evaluate this. Okay. Plus 1 over, there we go. Hopefully everyone sees where I'm getting these numbers. This should be negative 4 pi j. And so now I want to I want to do, hold on. Oh, and then it's f of 2. Okay. And so now, from this point, I want to do this. I want to combine these two so that it is 1 minus e to the -1 4 pi j. Oh, and this, recall, is that this is actually just 1. So actually, I can ignore that. So now we just get this. Oh, wait. And I'm pretty sure this is just almost at the answer. Now I take the magnitude of f of 2, and now I could move the magnitude to the numerator and denominator. Now this is equal to, the numerator is already positive, and so we keep that. And now the denominator is just 1 plus 16 pi squared, I believe. 1 square root. There we go. So 1 minus e to the -1, and then that at the denominator. And now we are done. Okay, any questions? I'm taking any questions. Sorry it took so long, but we're actually kind of on time as well. So any questions? I'd be happy to take anything. How does 4 pi turn into 1? Great question. E to the negative, like e to the 4 pi j is equal to 1. The same reason why e to the 2 pi j is equal to 1. Because remember, it's a complex exponential. This is like a you can just think of it as a rotating vector in the complex plane. And at degree 4 pi, it is just exactly pointing in this direction with magnitude 1. Hence, it's just 1. Questions? Questions, comments, concerns? I'll be sitting around until basically everyone leaves or I don't hear anything. But otherwise, please feel free to ask. I'd be happy to go back to any questions to clarify. I'll just be hanging around. Maybe I'll take another sip of. Okay. Yeah, of course. Happy to help out all the time. Okay. Oh, I'm glad. I'm very glad that everything's helping out. Otherwise, yep. All right. Thank you for coming.